In Lesson 1, Part 1, we looked out at the horizon, observed that it appeared flat, and with that observation, we formed the hypothesis that the Earth is flat. On the other hand, some people have gone out and observed the horizon and have seen curvature. With that observation, using the same reasoning, they are able to form a rivaling hypothesis that the Earth is a globe. Alright, so now that we've got two rivals, let's put our hypotheses to the test and see which is stronger. First, let's go take a closer look at this observation so we can see what we are up against. This observation comes from mctoon.net. mctoon is an anti-flat earther whose entire website is dedicated to combating the flat Earth hypothesis. He also has a YouTube channel dedicated to the same thing. Just so you know what you're looking at here, the red bars are simply just straight edges. They are meant to be a control in the experiment, representing a standard of flatness. Now, just basing it off of this observation alone, it looks pretty flat. But that isn't what he's basing his globe Earth hypothesis off of. Since the Earth is so big, he doesn't believe we would see much curvature this close to the surface. But he believes that if he scrunches the photo horizontally, it will reveal the hidden curvature of a globe Earth. Alright, here we are back at his website. I'll go ahead and scroll down here. There's his image. There we are a little bit more zoomed in. And this is where he has compressed his image horizontally. And lo and behold, we can see curvature. Here, I'll do the same thing for you so you can see what he did. Alright, this trick is really simple. All you do is select the horizon between the two beams, and then you grab it by the corner and scrunch it really quick. And then we can take a closer look here. Oh my goodness! You can see the curvature of the Earth! Or do we? Let's try this on the other side here. Okay, select it. Scrunch it. And take a closer look. What? Where's the curve? Why in the world is it curved on one side, but not curved on the other? I actually went and talked to mctoon about this, and he still thinks the right side is curved. So let's take this to the next level and measure this thing. This time, we are not going to scrunch the photo. We are going to measure the unscrunched photo so there can be no dispute about the scrunching process distorting the photo or the camera being tilted or anything like that. First, I'm going to sharpen this image by adjusting the brightness and contrast. This will make things easier to count the pixels as we measure the rate at which the horizon appears to curve. Alright, now here you can see I have measured it out to be just over 200 pixels. And here is where we can observe that this portion is all flat within 2 pixels. Let's continue on now, doing the same thing. Just zoom in here. Alright, now we'll adjust the brightness and contrast. Okay, now here I've measured it out. 100 pixels, 200 pixels, 300 pixels. And as we zoom in here, we'll see that it's gone up a pixel. So our rate of curvature is 1 out of 300 pixels. Now we're starting over. 200, 300, but it's still straight, so we'll continue on. 400, 500. Oh, now it's moving up. So our new rate of curvature is 1 out of 513. Starting over. 100, 200, 300, 400. And as we see, it's kind of in the middle of the beam, but it's still straight, so we'll keep going. 600, 700, 800, 915. We're definitely seeing curvature here, but it's curving at an uneven rate. Now, the brightness and contrast got a little messy over here on the right side, so we'll go ahead and readjust that so we can get an accurate measurement. Alright, here's that brightness and contrast. Looking much better now. It's still a little bit messy, but it's not too much to be worried about. It'll still work. Now, here you can see that I didn't number out the pixels this time. It was unnecessary because, as you can see, we can go all the way across this entire section and see that it is all flat within 2 pixels. So we saw an inconsistent amount of curvature on the left side of the photo, but on the right side we're not seeing any curvature at all. What is going on? Many globe earthers claim that because curvature was present, that automatically means the curvature was caused by a globe earth, and then that utterly destroys the entire flat earth hypothesis. But if that curvature was being caused by a globe earth, why was it so inconsistent? And why did it appear flat on the right side? It seems both hypotheses have a problem to deal with here. The flat earth has to explain the curvature, and the globe earth has to explain the inconsistency of that curvature and the lack of curvature on the right side here. So, what could be causing the appearance of this curvature on a flat earth? Here's a little something to remember. The moisture content and density of the air is not perfectly uniform. If the atmosphere is thicker on the left than it is on the right, then we won't be able to see as far on the left as we can on the right, and that is going to cause the horizon to appear to curve. In a way, the atmosphere on the horizon can act like a tree line. Here our tree line appears to curve in the grass because those trees on the left are closer to us than those trees down in the middle. Here's a nice condensed example of what I'm talking about. Here we can't see as far on the left as we can on the right, and that's causing a curve down in the grass there where the fog meets the grass. Here, I'll go ahead and draw that in for you. Going across, it goes up, and then it levels out again. Now let's go ahead and scrunch other horizons and see what happens. Okay, select. Scrunch. Okay, let's zoom in and I'll move over for you. Huh. Look at that curve. Are you going to say that was the camera being tilted? Is that lens distortion? I don't think so. Pretty sure that's the atmosphere. Ooh, here's a nice pretty one, taken from above the clouds. Select. Scrunch. And does that look like it proves that the Earth is a globe? No, it just proves clouds are uneven. Let's try this one. It looks like it was taken from a plane, and a lot of people claim to see curvature from planes. Select. Scrunch. Where's the curvature? Ah, I love this one. All right, select. Scrunch. Whoa! Look at that. Okay, well, the camera probably wasn't perfectly level on that one. I can see that, but it still looks pretty flat. All right, so we can fully acknowledge that we can sometimes see curvature on the horizon. But does that mean the Earth is a globe? No. Other things can most certainly cause the horizon to appear curved. Curvature does not equal globe. And because horizons still generally appear flat, our hypothesis still stands. But now it has additional fortification because of our further observations. In other words, our hypothesis has withstood this test. Thank you all for watching. If any globe earthers would like to explain these uneven amounts of curvature, or the flat horizons that we saw, I will allow you to do so in this comment section, so long as you can be respectful and maintain a friendly demeanor. Though, I would really love to see your explanations on our debate board. There's a link to that down in our description. In Lesson 1.1, based on evidence, we formed the hypothesis that the Earth is flat. In Lesson 1 Part 2, we acknowledged that sometimes the horizon does appear to curve. However, we pointed out that just because we can sometimes see curvature, that doesn't automatically mean the Earth is a globe. With that, our hypothesis still stands, and now it has been expanded, acknowledging that different factors can sometimes cause the flat Earth to appear to curve. Now, as many already know, a frequent factor that causes horizons to appear to curve is a camera's lens distortion. When someone shows you a picture of a curved horizon, this is something important that should be taken into consideration. Neil Tyson was smart enough to acknowledge this when he spoke of this Red Bull drop photo.
Show us where the International Space Station is, Hubble, etc.
Okay. So if the Earth were actually this size, the International Space Station would be orbiting about a half an inch above the surface. And that dude who jumped out of a perfectly good balloon, what's his name? Felix Baumgartner. He would have been about 2 millimeters above the surface of this globe. That's his edge of space jump. Now, you know, I don't. It's fine. He wants to. I don't have a problem if he does it, but the honesty of it would greatly diminish what I think people thought he was actually doing. And not only that, they made sure to photograph him standing there with a really wide-angle lens, which curves horizontal lines. So in the photo, you see this curvature of Earth's surface, and he said, "Wow, he's in space. Look at that." No, he's not. At that height, you don't see the curvature of the Earth if you are 2 millimeters above this beach ball. You just don't. That stuff is flat. And then I showed examples of wide-angle lenses curving horizontal. I tweeted that.
You did.
But I don't want to be a spoil, curmudgeon or anything. I just wanted to put. I don't.
Lens distortion doesn't just happen with wide-angle lenses. Here, Jeranism took a picture of his granite countertop with a pretty ordinary lens. Now watch what happens when he scrunched the image just like we did in Lesson 2. Boom! After scrunching his level countertop, it appeared to curve because of lens distortion.
And for the ultimate proof, watch this. I drew this image, which is just a white line, perfectly straight, drawn on a completely black background. I then open it up on my computer and take a photo of it from a camera. I then condense it, and the straight line is curved. But it's a straight line, we drew it. Oh boy.
Every good hypothesis should have disconfirming evidence, a means whereby it can be proven wrong. So with that being the case, if you want to prove the curvature on the horizon is caused by the curvature of the Earth, and prove our hypothesis wrong, there are some expectations that you need to meet. First, if you're going to show us curvature in a photo, you need a control measure to rule out the lens distortion. We can call that expectation number 1. A flat Earth opponent by the name of Mr. Sensible did an excellent job of meeting this expectation when he used a set of strings as a control measure. With this, the rule was the horizon could not be any more curved than the strings were. If the horizon was more curved than the strings were, it could not be because of lens distortion. This is because With lens distortion, the center lines are never more curved than the outer lines. So when Mr. Sensible attached his camera to a balloon and launched it over 37,000 meters into the air and found some curvature, we couldn't say it was because of lens distortion, because he fulfilled expectation number 1. With that, he thought curvature equals globe, therefore he wins.
Now this drop-dead gorgeous image is at 35,160 odd meters. It is stunning. There is no doubt that there is curve there. That horizon line is across the middle of the field of view, so barrel distortion up or down is not going to be taking effect. That is a smoking gun. But let's have a look at it compressed. And I'll add a horizontal yellow line again for completeness. Oh look, we done got curve. I'd say it's game over for flat Earth.
But remember, in our last lesson we mentioned how the presence of curvature doesn't automatically mean the Earth is a globe. There were still more expectations that he did not fulfill. As we mentioned in our last lesson, the atmosphere can also cause our horizon to appear to curve. This also needs to be factored out. A simple way to do this is to determine if the horizon has the same amount of curvature all the way across. We checked for this in our last lesson when we measured the curve in this image and found that the left side was more curved than the right side was. Notice here how MC Toon also had a means of ruling out lens distortion. However, he failed when it came to meeting the second expectation. To be clear, expectation number 2 was to rule out the atmosphere by showing a consistent amount of curvature. Let's see how Mr. Sensible did at fulfilling this expectation. Adjust brightness and contrast. Alright, now we're going to zoom in. We can see those pixels. We can see that rate of curvature over here. We can measure it out if we wanted to or needed to. But as we go all the way across, all of a sudden we start getting these big long stretches of straight horizon. So that's not showing us a consistent amount of curvature. It's a lot flatter over here than it was over here. So with that, Mr. Sensible failed to meet expectation number 2. On that same note, I want to point out a different way curvature is being created in this image. I'm going to go ahead and put a red arrow right where we see the horizon line. I think that's pretty good. Now I'm going to adjust the brightness and contrast, and we're going to see if that... You'll see here that our horizon line is suddenly rising now. Going up and up and up. And if I go the other way, it's going to lower. And the reason why this is happening is because this curvature that we're seeing is not being caused by the curvature of the Earth. It's being caused by the light reflecting off of the atmosphere, the sun's spotlight. And this can be seen even stronger when I adjust the brightness and contrast, and you can see the bottom part of our spotlight, the ring or circle. You can see the spotlight effect going up. There you go, on the bottom there. I guess that's... There you go. Here I'm trying to point out the bottom curve of the sun's spotlight. Now let's compare that to the horizon we see on this ball. I'm going to go ahead and adjust the brightness and contrast on that. Black and white. And notice how our horizon line doesn't appear to move around. It's staying in the exact same spot. And that is because our horizon is being created by the curvature of the ball. So here Mr. Sensible failed expectation number 3, ruling out the atmosphere by showing us a hard horizon line that doesn't move when you adjust the brightness and contrast. Although, you should also keep this in mind. Please notice how this flat stage appears to curve when you shine a circular spotlight on it. Now watch what happens when we adjust that brightness and contrast. That horizon line doesn't appear to be moving anywhere. So that's definitely something that should be taken into consideration. Oh, now it's moving somewhere, but not very much, just a little bit. We'll call this expectation number 4. If you want to prove that the curve is being created by the curvature of the Earth, you need to prove that the spotlight effect is not taking place. Expectation number 5 applies more to video footage. It states, curvature should gradually become more and more visible at a consistent rate as you rise in elevation. So when Mr. Sensible's horizon at 25,000 meters was flatter than it was at 15,000 meters, Mr. Sensible failed to meet that expectation. All in all, I can describe all of this as a successful parry. Our hypothesis has withstood Mr. Sensible's balloon test. However, we haven't proven our hypothesis true yet. We haven't yet defeated our rivaling hypothesis that the Earth is a globe. But our hypothesis that the Earth is flat is still standing and is able to continue on to the next bout. That is something. However, the main thing I want you to remember from this lesson is our list of expectations. The things that would disconfirm our hypothesis. There are also additional expectations after this, but we'll talk about those later on as we talk about the z-axis. We'll also be providing some additional evidences and be proving some points as well, so I look forward to that. Until our next bout, thank you for watching. If you are one of those people out there still claiming you can see curved horizons on the x-axis, this video is especially for you. Alright, let's keep things simple and straight. This hula hoop represents your horizon. At eye level, you can look all the way around you and not see any curvature. Now, let's see what happens when we give it some curvature. Whoa! What happened to the horizon in back of you? Notice how in order to get just that little bit of curvature here in front, you had to significantly drop the horizon in back of you. Please note and remember this. If you were to see the curvature of the Earth at eye level in front of you on the x-axis, that would mean when you turn around to see the horizon in back of you, you would have to look down in order to see it. And the bigger the hula hoop, or the farther away that horizon is in front of you, the bigger that drop would be in back of you. That is something we do not see anywhere on Earth. Thank you for watching. In Lesson 1, we shared the observation that the Earth appears flat. In this lesson, we are going to share another observation and weigh our hypothesis between the two observations. Okay, so here are the things to remember. Our first observation is that the Earth appears flat. Then we have our hypothesis, which is that the Earth is flat. It doesn't just appear flat, it is flat. Alright, observation number 2. Here is the famous observation of a ship appearing to sink as it goes over the horizon. A great many people instantly think of this example when trying to prove the shape of the Earth. Now let's take a closer look at this observation. Let's take the X, Y, and Z axes into consideration here. This boat appears to be sinking on the Y-axis as it travels away from us on the Z-axis. However, when we see this phenomenon, do we ever see any curvature on the X-axis? Remember, observation 1 was that horizons appear flat. In other words, observation 1 is that we do not see curvature on the X-axis. So when we see curvature in one direction, but don't see curvature in the other direction, what shape do we get? Do we live on a roll of toilet paper? Let's think about this further. Here is a diagram looking down on an observer from above. What if our observer were to turn their head 90 degrees and see a boat appearing to sink in the other direction? Then what would happen? Well, then you would just be moving your Z-axis and you would have the same problem over there. No matter which way you face, you would still see apparent curvature on your Z-axis, but no curvature on your X-axis. If we saw Z-axis curvature in all directions, but no X-axis curvature, it would appear like we live in a giant ripple. Perspectively, the ground appears to rise up to our eye level. This perspective really throws me through a loop when I put on a new pair of glasses after not having worn them in a long time. It feels like everywhere you walk, you are walking uphill. So why do horizons appear to rise up to eye level? Is it the curvature of space-time around you? The YouTuber Jeranism does an excellent job at describing how this works in linear perspective. I'll put that next on this course's playlist as a Lesson 2 extension video. Because horizons appear flat, we hypothesize that the Earth is flat. Now here we make a prediction. Boats don't appear to sink on the horizon because the Earth is curved. Boats actually appear to sink on the horizon because of the effects of the atmosphere. We'll talk about the effects of the atmosphere in Lesson 3. Until then, catch you in the next lesson. Thank you. How do you know if your horizon is at eye level? Here is an interesting way to determine that. Here I have taped a small piece of paper to a door directly in front of my eye. The paper represents my eye level, seeing how it is at the exact height of my eye. This door is at the end of a long hall with a level floor and a level ceiling. Here you can see that little white paper at the very end of the hall on the door. Now check this out. All of these lines point right to that little paper on the door at my eye level. This isn't a fluke. If a short person were to try this, the results would be the same. So long as your lines are level, you will find that vanishing points are at eye level. Now let's take this outside. Here we are standing under a pier. Boom! All of our lines converge right at the vanishing point, and our vanishing point is at eye level. Now, because our vanishing point is on the horizon, we can know that our horizon is at eye level. Now, is this always the case? No. The weather can very much obscure our horizon and make it appear below eye level. It can be kind of tricky sometimes, but hopefully you get the idea here. Thank you for watching. The number one error people make when making claims about the horizon is not taking the effects of the atmosphere into account. The Earth Curvature Calculator is a perfect example of this. So, this is the Earth Curvature Calculator, and what you do here is type in your eye height and how far away your target is. After pushing calculate, it then tells you how far away your horizon is and how much of your target gets covered by the curvature of the Earth. Here is the diagram it shows. The dotted line represents your line of vision. The blue arrow represents your eye height, and the red arrow shows you how much of your target gets covered by the curvature of the Earth.
What are you arguing? Where did it go wrong?
This calculator's math, as perfect as it may be, is built upon two fatal assumptions. I'm only going to talk about one of them here, and that is that light travels in straight lines.
Wait a second. Fatal assumptions? Are you telling me that light does not travel in straight lines?
That is exactly what I'm saying, and here I'll show you why. To put things more clearly, the Earth Curvature Calculator assumes there is no atmosphere on the face of the Earth. And the atmosphere bends light. The first way it bends light is through reflection.
Okay, explain reflection.
Alright. Boom! Reflection! That fog is white because it is reflecting all that light back at your eye.
Wow, that is a lot of reflection. I can see all that.
Calculator didn't see that coming.
I guess you have a good point.
Now, how far away do you think that horizon looks to you?
Definitely not as far as that ocean view I saw the other page.
According to this, that horizon line should be 2.999, about 3 miles away. That horizon is not 3 miles away. And you can't tell me that those cars over there are hidden because of the curvature of the Earth. Strike one for reflection. Next, we have something called refraction. Now remember, the fatal flaw of the calculator is that it assumes that light travels in straight lines. Here, we can see the appearance of water on the road, but it's not really water, and it's not being reflected. Reflected light is light that bounces off another surface. This is light being bent up towards your eye due to something called refraction. This diagram is pretty good at showing you what's going on. The light from the sky is coming downward toward the person and is being bent upward by the hot air, which has a different density than the cool air above it. And so it goes upward towards his eye. And it looks like water there on the ground, which is just a reflection of the sky. When many people think of refraction, they often think of this classic example of the straw that appears to be broken in a glass of water. But refraction takes place in more than just this example. It also takes place in the sky. This kind of refraction is called an inferior mirage, and it can alter how far away your horizon appears to be. Can you imagine if that mirage covered the entire width of this picture? Imagine that car not being there. That horizon line is going to look a lot lower, isn't it?
Definitely, I can see that.
That is basically what's going on in this picture. This is called a theta mirage.
Theta mirage. It's interesting. It looks like the boat is floating in the sky.
But it's not really, it's actually sitting on water. But the mirage is obscuring your view of that horizon line. Now this is called a superior mirage. And what is going on here is light is being reflected off of that boat, it's going up into the sky, and is being refracted downward towards your eye.
What in the world? I could not figure out what was going on with this picture. It's like two images reversed.
Yeah, it's just a copy of that boat, upside down. So as you can see, atmospheric refraction can make it rather difficult to see exactly how far that horizon line is.
Wow, it looks like that boat is like, either the horizon is really high or a lot lower.
This just shows different intensities of that refraction level, if that makes any sense. A little while ago, ABC News reported on being able to see the city of Chicago from all the way on the other side of Lake Michigan.
All the way on the other side of Lake Michigan? How far away is that?
According to the report, that image was taken from 53 miles away.
53 miles away? How is that even possible? Can we put that in the calculator?
Sure thing. Now, that photographer was down on the shoreline, and even if his eye height was 20 feet high, with a distance of 53 miles, that city should be covered by 1,506 feet of curvature.
They've got some really tall buildings over there.
But none of them are that tall. The Earth curvature calculator was definitely wrong that day. This is another kind of atmospheric refraction. It's called heat haze. Does the light look like it's going straight to you here?
Not at all. It looks like, I guess it has the kind of same effect of looking through a fire. It just kind of distorts your vision.
But those light rays don't look straight.
I guess not. You're right.
Atmospheric refraction happens because of these three varying factors. And there is never a day where they don't exist in the sky. And there is never a day where they are exactly the same throughout the entire sky. The sky is huge, and temperature, pressure, and humidity change with elevation. With that being said, strike two for atmospheric refraction. Another way light is bent in the sky is atmospheric diffraction. Atmospheric diffraction causes these rings of light around the sun and the moon. My main point being here that this is an example of light not traveling in straight lines because of the atmosphere. As light touches the edges of the water droplets in the air, it gets bent and scattered into different directions. And that's atmospheric diffraction. With that, strike three for atmospheric diffraction, bending the light in the air. In summary, light cannot travel in straight lines through the atmosphere because of reflection refraction, and diffraction.
I like how you say light cannot travel in straight lines. I mean, maybe it would if there was no atmosphere, but the Earth is full of atmosphere. So I can definitely see what you've got going on here. I think we've debunked the Earth curve calculator.
Put a fork in it. It's done. Thus perished the Earth curvature calculator. Reading through the comments, there are a number of globe earthers who claim we are wrong and accuse us of acting like there is 100% humidity all of the time when we refer to atmospheric refraction in our explanations. They claim atmospheric refraction does not happen in the desert and other hot, dry places. We're going to put the kibosh on that real quick. Does atmospheric refraction happen in hot, dry deserts?
I'm right here. Mama, I'm coming. Mama, I'm right here. Mama, I'm coming. Mama, Papa! Mom!
Oh my goodness! Were they acting like there was 100% humidity in the desert? No. Deserts are extremely famous for mirages, and mirages are caused by atmospheric refraction. The atmosphere does not need 100% humidity in order for refraction to occur. Thank you for watching. Back in 2017, a YouTuber by the name of Soundly featured this observation of the Lake Pontchartrain pylons in an effort to debunk the flat Earth. The Lake Pontchartrain pylons are in a straight row across a 15-mile stretch, and because we can see them curve, people instantly assume that it proves the Earth is curved. Please remember our prediction at the end of Lesson 2. That prediction was that the curvature we see is not caused by the shape of the Earth, but by the effects of the atmosphere. Let's examine this observation closer and see if our prediction holds true. Is there anything here that supports our prediction? Let's zoom in here. What kind of curvature is that? I give you the edge of the flat Earth. It's curving around it. Just kidding. Notice how there appears to be more curvature at the bottom of the pylons than there is at the top of the pylons. That is a key indicator that tells us the curvature we see is caused by the atmosphere. I really like this image. It comes from the YouTuber Phuket Word. He shared this observation of how we can see the same curving effect on the guardrail of a straight road. Take notice of that same extreme curvature at the bottom of the rails and that gradual curvature at the top of the rails. For a little bit more background information on this image, his camera is pretty much on the ground in the middle of the road. Here's a picture of the road when he stands up. Please take notice of how all of the curvature you just barely saw is gone. I really want you to go and see his video for yourself, because it is phenomenal at proving how it is the atmosphere that causes things to appear to sink on the horizon. We will leave that for you next on the playlist. Please be sure to give it a like. We'll also leave a link to Soundly's channel in this video's description, so you can see more of his Pontchartrain images for yourself. Please leave him a like also, for we wouldn't have this atmospheric evidence were it not for him. He's got some great stuff there. Thank you for watching. Okay, here's a quick recap on everything we've gone over so far. In Lesson 1, we covered how we know the Earth is flat. In Lesson 2, we covered the whole boats appearing to sink on the horizon thing, and explained how we do not live on a toilet paper roll. In Lesson 3, we explained the effects of the atmosphere and how they can cause boats to appear to sink on the horizon. In this lesson, I'm going to be talking about the sun, and how the same thing that causes boats to appear to sink on the horizon also causes the sun to appear to sink on the horizon. So, what causes boats to appear to sink again? It is the same thing that causes boats to appear to fly on the horizon. It is atmospheric refraction. The sunlight gets bent as it travels through the atmosphere, and when none of that light is able to reach you, the sun can no longer be seen, and you are left in darkness. Now, do you remember that whole atmospheric reflection thing I mentioned in Lesson 3? Another name for this is atmospheric opacity. The more atmosphere you look through, the harder it is to see through it. It becomes less transparent. The same concept applies when it comes to atmospheric refraction. The more atmosphere you look through, the more ability that atmosphere has to bend the light that passes through it. Now, consider the distance of the sun and the distance of this boat. If the reflected light from this boat can get refracted this much over a relatively short distance, how much more should the light from the sun be able to get refracted over a much greater distance? People ask, if the Earth is flat, why does the sun light up the mountain tops before the mountain bottoms? A similar question is, if I am sitting on the beach and watch the sun set, why can I stand up and watch the sun set again? Let's see if we can't use the principles we learned in Lesson 3 to answer these questions. In Lesson 3, we learned about these 3 atmospheric factors that limit our range of vision: atmospheric reflection, refraction, and diffraction. These factors make it so the lower you are in altitude, the more limited your range of vision becomes. This is because the lower and lower you get, the denser and denser the atmosphere gets. Phuket Word beautifully demonstrated this for us in our Lake Pontchartrain portion of Lesson 3. Here his camera is on the road with a limited range of vision due to the atmosphere. Next, he lifted his camera up to eye level, providing us with an extended range of vision due to the variance in atmospheric density. Now, here's something that just might save your life someday. People die every year due to something called altitude sickness. It is caused by rapid exposure to low amounts of oxygen at high elevations. This can create an excess amount of fluid in the lungs or in the brain that can become fatal within hours. If you would like to learn more about that, we'll leave some links for you in the description. So why does the light touch the mountaintops first at sunrise? It is because the atmosphere is less dense up there, allowing the sun's light to reach farther. It's as simple as that. Thank you for watching. In Lesson 4, Part 2, we talked about how the sun hits the mountaintops first at sunrise. In this lesson, we're going to pull out our magnifying glasses and take a closer look at the mechanics behind that. Khan Academy teaches a really excellent lesson about refraction. Let's highlight some of that and build on it in the context of a flat Earth.
In the last couple of videos, we talked about reflection, and that's just the idea of the light rays bouncing off of a surface. And if the surface is smooth, the incident angle is going to be the same thing as the reflected angle. We saw that before, and those angles are measured relative to a perpendicular. So that angle right there is going to be the same as that angle right there. That's essentially what we learned in the last couple of videos.
All right, so this is Lesson 3 on their series on reflection and refraction. In Lessons 1 and 2, he explained how there are two different kinds of reflection: specular reflection and diffuse reflection. Specular reflection is a uniform reflection. It is the kind of reflection wherein you see a mirror image of something, like you see the image of this hill in the water. Diffuse reflection is reflection that is too scattered to reflect an image. In this picture, you can see the water reflecting the sun's light, but the light is too scattered to form a mirror image of the sun. In his example here, he is talking about how light reflects off of water, but we are going to look at how this applies to the atmosphere. Is the atmosphere dense enough to reflect light? Yes, this is an example of diffuse reflection. You can see the light, but it does not produce a mirror image of anything. Notice how the lower and lower you look in the sky, the wider and wider the sky gets. This is because more and more light is being diffusely reflected by the thicker and thicker atmosphere. We often refer to this as atmospheric opacity. Our atmosphere is a gradient. In our last lesson, we described how people can die of altitude sickness due to this atmospheric gradient. We also attributed this atmospheric gradient as to why the light touches the mountaintops first at sunrise. Globe earthers acknowledge how the atmosphere reflects light and make a big deal about it. That is what makes the ozone layer so important: its ability to reflect dangerous radiation. Enough said on that. Water reflects light, and so does the atmosphere. Let's continue. Next, he talks about refraction and how the path of light gets bent when it travels from a less dense medium to a denser one. Pay attention to the way he describes things here. Now, he is a little long-winded, so I've sped things up to help him be a little quicker in getting to the point.
But when you think about refraction, I actually like to think of it as kind of as a bit of a vehicle. And to imagine that, let's imagine that I had a car. So let me draw car. So we're looking at the top of the car. So this is the passenger compartment. It has 4 wheels on the car. I'm looking at it from above. And let's say it's traveling on a road. It's traveling on a road. On a road, the tires can get good traction. The car can move pretty efficiently, and it's about to reach an interface. It's about to reach an interface where the road ends, and it will have to travel. It will have to travel on mud. It will have to travel on mud. Now, on mud, obviously, a tire's traction will not be as good. The car will not be able to travel as fast. So what's going to happen? Assuming that the steering wheel isn't telling it to turn or anything, the car would just go straight in this direction. But what happens right when which wheels are going to reach the mud first? Well, this wheel right here is going to reach the mud first. So what's going to happen? There's going to be some point in time where the car is right over here, where these wheels are still on the road. This wheel is in the mud, and that wheel is about to reach the mud. Now, in this situation, what would the car do? What would the car do? And assuming that the engine is revving and the wheels are turning at the exact same speed at this the entire point of this the entire time of the simulation. Well, all of a sudden, as soon as this wheel hits the medium, it's going to slow down. This is going to slow down, but these guys are still on the road, so they're still going to be faster. So the right side of the car is going to move faster than the left side of the car. So what's that going to happen? I mean, this is you see this all the time. If the right side of you is moving faster than the left side of you, you're going to turn, and that's exactly what's going to happen to the car. The car is going to turn. It's going to turn in that direction. And so once it gets to the medium, it'll now travel. It'll now turn from the point of view from the car turning to the right, but it'll now travel in this direction. It will be turned when it gets to that interface. Now, obviously, light doesn't have wheels and it doesn't deal with mud, but it's the same general idea. When I'm traveling from a faster medium to a slower medium, you can kind of imagine the wheels on that light on this side of it, closer to the vertical, hit the medium first, slow down so the light turns to the right. If you're going the other way, if I had light coming out of the slow medium, so let's imagine it this way. Let's have light coming out of the slow medium. And if we use the car analogy, in this situation, the left side of the car is going to, so if the car is right over here, the left side of the car is going to come out first, so it's going to move faster now. So the car is going to turn to the right, just like that. So hopefully this gives you a gut sense of just how to figure out which direction the light's going to bend if you just wanted an intuitive sense. And to get to the next level, there's actually something called Snell's law. Snell's law.
So, refraction happens because light is getting slowed down as it travels into a denser medium. Now the question is the atmosphere dense enough to slow things down? Well, yeah. Things burn up in the atmosphere all the time due to air resistance. If I stick my hand out on a car window, I don't have to be traveling very fast before I can start feeling the wind pushing back on my hand. In a way, it kind of feels like the resistance you feel when you wave your hands through water. Now imagine how much air resistance you would experience traveling at the speed of light. Talk about an enormous belly flop. So atmospheric refraction is very much a thing, and people should take it into account when it comes to the setting sun. Now, let's not forget how the atmosphere is a gradient, and how the lower the atmosphere is, the denser it gets. And the denser it gets, the more it is able to bend light. Check it out. This globe earther gets it. Thank you, Fortuna Pix, for making this awesome animation. So the atmosphere is able to refract light. The atmosphere is also able to reflect light. And when you take both of them into account, this is what you get. That looks exactly like what we see going on here. Let me explain. This is how globe earthers describe the sunlight hitting the top of a mountain first at sunrise. Our observer is the little red dot, standing in the shadow of the earth, and observing the sun hitting the top of the mountain. Now, allow me to remove that mountain here for a second, and let's observe the light in the sky. When our observer looks east, they're going to see a bunch of light in the sky. And the further west they look, the darker the sky is going to get. Note how we can zoom in on this all you want, but we are still going to get the same effect. Is this something we can observe in real life? Okay, here we are looking east at all the light in the sky right before the sun comes up. All right, now we're going to go look above us and see how the sky is getting darker up there. Now we're going to go look out west. Notice how the sky starts to get lighter, and then it starts to get darker way down there in the distance. So we were able to look east and see a bunch of light in the sky. But according to this model, the west should be a lot darker than what we are seeing in real life. Oh, but what about refraction? If the light gets refracted, then the west will appear to get lit up as well. Ah, yes, the west will get lit up, but so will our observer. Do you see the problem here? Now let's take a look at how this works on the flat Earth model. This is a basic diagram of what we can observe. The sun gets refracted downward by each layer of the atmosphere, like we saw in the refraction video. In the meantime, each layer also reflects light back upward. In the flat Earth model, the sun's light has a limited range due to refraction. This line here represents the edge of the sun's direct range. Now, let's add our observer as the red dot here, and throw in a mountain behind him. Here our observer is in the dark. None of the sun's direct sunlight is able to reach him, and the primary reflection from that direct sunlight is not able to reach him either. Our observer is not in utter darkness though. He is still receiving some light, but it is from secondary and tertiary reflected light, rather than primary reflected light. In other words, our observer is receiving a reflection of a reflection, or a reflection of a reflection's reflection, creating the diffuse reflection we saw in the sky when we looked east before the sun came up. The top of our mountain, however, is receiving a nice strong primary reflection, which lights it up quite nicely. Now, what is the sky going to look like for our observer under these conditions? If this is just before sunup in the morning, the sky will look brightest to the east, as we saw. It will then appear to get darker above you because there is less atmosphere up there to reflect the light back down to you. And angles may have something to do with that as well. Then, out west, you're going to notice the sky getting bright again because you are looking through more atmosphere, which is able to reflect a greater amount of light. And then you will notice it gradually getting dark again. Exactly what we saw in real life. It works perfectly on a flat Earth, but it doesn't work on a globe. Not without putting our observer in direct sunlight. Go see it for yourself. There are a lot of cool places to watch the sunrise. Here I found a neat 360 video of a sunrise on Punta Cana Beach. I'll leave a link for you in the description. But check out that gradient. The gradient in the sky is even easier to see when you put it in black and white. And here we are looking west. Thank you for watching. May God bless your studies. In a recent interview, our guest, Flat Earth Math, provided an observation of the sun not appearing to shrink as it traveled across the sky. Here you can see his photo at noon, lined up against his photo 21 minutes before sunset, wherein you can see that the sun appears to be the same size in both photos. Many people have observed this, both with and without a solar filter. And many people claim that this is solid proof that the Earth is a globe, and that this observation would be impossible on the Flat Earth model. Strawman alert! Whose Flat Earth model are they talking about? Herein, globe earthers tend to invent their own faulty model and then say, see, it doesn't work. Please note how in Eric Dubé's explanation, we saw the sun appear to set, but we didn't see it appear to shrink. Note how the sun doesn't appear to shrink here. Nor do we see the sun appear to shrink here. Just exactly where does he say the sun is supposed to shrink? What Eric Dubé didn't explain was why the sun didn't appear to shrink. Rob Skiba, on the other hand, did explain that.
The atmosphere, especially over water, is made up of zillions and zillions of tiny convex drops of water. Then, collectively, perhaps they all combine to make one big convex lens, in which case it would act like a magnifying glass. Okay, so with that in mind, let's look up some websites dealing with the refraction of light. You might see a graphic something like this, showing light bending downward. And now we've all seen pictures of, a pencil or something in a glass of water, and how not only does refraction bend the image downward, it also magnifies it. I'm going to say that again. Water causes refraction, bending the image downward, and magnifies it.
Now there is something else I want you to take into consideration. Here is a yardstick on the floor. Now watch this ball shrink as we move it across the yardstick. This is what globe earthers claim the sun should be doing on a flat Earth. Alright, now here is a yardstick on the ceiling. Now watch as this ball moves across the stick on the ceiling. Does it appear to shrink to you? It's moving the same distance. Now where do we see the sun? On the floor or in the sky? Can you see how people either intentionally or unintentionally misrepresent the flat Earth here? They act as if the sun would have to be on the ground in order for the flat Earth model to work. Now I know many people are going to look at this yardstick and say, oh, well that ball is barely going a few feet. That is hardly going all the way across the ceiling. But the fact is, we really don't know just how far the sun is actually moving. If we were to look through a microscope and see something move all the way across our view, we would say, wow, that moved a lot. But if we step away from the lens, our view changes, and we will see that the thing barely moved at all. We simply don't know how thick the firmament is, and if the sun is in the firmament or above the firmament, we have no way of knowing just how much it is being magnified. Therefore, we just don't know how much the sun actually moves. To our knowledge, no one has gone up to the firmament and tried drilling through it to see how thick it is, though we do know people have thrown several nukes at it. To learn more about the firmament, please see Lesson 7, Part 2, and the lessons that follow. There's a link in the description that'll take you there. While we don't know everything, that's okay. Just remember what we don't know doesn't invalidate what we do know. And please beware of the incredulity fallacy. Just because we might not be completely sure as to how something works, that doesn't mean we are wrong. Having said all of that, when people argue that the sun's apparent size disproves the flat Earth, we disagree, and we acknowledge that claim as a straw man argument. This has been Professor Kyle Adams of the Flat Earth Institute of Science. Thank you for watching.